like scientific visualization, information visualization, performance visualization, and software visualization. So I guess, well, also right at the outset, I can tell you that I'm not a hacker. And I also saw a person wearing a t-shirt with Misfits written on the back, so I feel the same. So in this talk, I'm going to talk about the basics of visualization.
Would you mind holding the microphone just a little bit closer?
Okay. Is it better?
Yes, good.
So in this talk, I'm going to talk about visualization, the basics of visualization. Why do we need visualization? Then what are the different types of visualization? And then I'll provide a few examples of visualization where throughout my graduate studies, I've looked at different visualization problems. And then finally, I'll conclude with the kind of visualization problems that the research scientists are looking at right now. So let's say now this is, so these numbers represent temperature conditions through a particular area. And let's say if I ask you to find out, okay, what's the maximum temperature? So what you're going to do is you're going to go through this table serially and try and find out which is the maximum number. And let's say if I tell you to find a range of the temperatures, so it's going to be hard just by looking at these numbers in order to find that range. So what we can do in this case is, so we can color code the temperature conditions such that the blue colors represent low temperatures and the pinks represent, and the pinks and the purples represent high temperatures. So here you can see,
he hit you.
is there a
That was the eject button.
pointer?
You actually just blew up my underwear.
Is there a pointer here?
Yeah, yes, yeah, that. Yeah.
So here you can see the maximum temperatures and the range, so on and so forth. So these are low temperatures. The blues, the greens represent the medium temperatures, and the reds and the purples represent max temperatures.
Does that match the prior slide?
What's that?
Do those color layouts match the prior slide?
Yeah.
I sure do. Yeah. I didn't notice it. My visualization was off.
Are you colorblind?
No. I just hadn't noticed
Some
the
people
pattern.
are. They just
I was trying to
don't
see
know.
the pattern of the high numbers versus the low numbers, and I hadn't noticed that when I looked at it. I thought it was a little different.
So what is visualization? So visualization is an area of computer graphics that deals with the management and presentation of information in a visual form to facilitate rapid, effective, and meaningful analysis and interpretation of the data. So what are the advantages of visualization? It's used in handling high information densities, then in making important decisions where time is a critical factor. Then it is also used in user collaboration, where the user interacts with the data to provide domain knowledge. And a few more definitions about it. And then visualization is used in different areas, such as physical domains, such as geographic information systems, weather satellite information systems, and in abstract domains, such as software visualization, data mining, and network security. So let's look at a mathematical definition of visualization. So let's say you have a data set D, which consists of n elements, and each element has m attributes. So this is a multidimensional data set that we're talking about. So what is visualization in that case? So in that case, visualization can be defined as the mapping between the different visual features to the different attributes. So visualization is the selection of a mapping.
Hip-hop music.
It's a head. Is it okay? Can you guys hear me without the black helicopter noise?
Yeah.
Okay, well, I'm going to hand this copy.
We don't talk about black helicopters.
Sorry about that. Okay.
What size?
Yellow.
Just speak up, yeah, we'll be good.
Okay. So visualization is the selection of a mapping between the different attributes and the visual features, and the evaluation of a viewer's ability to see that, to see the images generated by that mapping. So, and I'll provide a few more examples about that, so the mathematical definition would get a little more clearer. So now this is the visualization pipeline or the visualization process. So let us look at the different building blocks of visualization. So visualization can be considered as the path from data to understanding. So the different blocks in a visualization are the raw data, which can be in the form of binary data, text files, volume data, whatever kind of, then medical data, whatever kind of data you can think of. And that data needs to be converted into data tables. So the data tables can be considered as an Excel spreadsheet, whereby the different columns of that spreadsheet represent the different attributes of the data. So that is a multidimensional data set. And each row represents one particular data element, which consists of multiple attributes. So you convert the raw data into data tables using some kind of data transformations, such as selection, projection, aggregation, and whatnot. And then you have those data tables. So you have the data tables, that is the data attributes. You map those data attributes to the different visual features. In the visualization community, we use different visual features, such as the spatial position, where exactly the data element is to be positioned. Then different texture properties, such as size, orientation, then different color properties, such as hue and luminance, then different shapes, and different properties of motion, such as this is flicker, this is direction of motion, and this is the velocity of motion. So you map the data tables to these different visual features. Now there is a science behind that, which we call as perceptual guidelines. We use something called as perceptual guidelines in order to map these different data attributes to the different visual structures. So what I mean by perceptual guidelines is that different visual features are perceived differently by human beings. Now, for example, like a user sees the luminance patterns first before he sees the hue patterns, and then so on the texture patterns. So whatever important data attributes you have, you map those to luminance first. Then thereby, as the order of the data attributes decreases, you map them to hue, then to various texture properties, then to various motion properties.
Yeah, I actually I did a talk last night and actually mentioned RGB, and it was not about this. I mean, but it actually had like one or two statements, and it did mention that humans do see the change in luminance more than variations in color.
Right.
Yeah, so this reaffirms that.
Well, so therefore, now let's say like you have color patterns which have different luminances and hues. So you're going to see the different luminance patterns first, then the hue patterns. So in a visualization, in different visualizations that we build, so we make sure that if we want to see the different hue patterns, we make sure that the luminances of those different hues are same, so that that thing is eliminated, that, okay, the luminances are the same, so whatever differences we are going to see is only based on the different hues. Okay, so the data tables are converted to visual structures, and then the visual structures are converted into visualizations, which can be static visualizations, such as an image shown here, and dynamic visualizations, as I'll give a demonstration later on. And hopefully, the visualizations, that is the images generated by these mappings, will help the user to explore, analyze, and discover within their data. And hopefully, he'll be happy at the end of it. The user can also interact with the visualizations by translating, zooming, then with intelligent camera planning techniques, and so on. So let us look, now visualization is broadly classified into two different kinds. One is scientific visualization, which is the display of physically based data. That is, the data has inherent geometry in it, such as geographic information systems, molecular biology. Now for example, this image shows the hurricane patterns. Now, this data has inherent geometry built in it. Now let us look at the other type, which we call as information visualization. Now in this particular kind of visualization, there is no inherent geometry behind the data. So basically the data is abstract, such as software visualization, such as software data, then data mining data, then file system structure. So this doesn't have an inherent geometry in it. We, the visualization experts, or like whoever is building the system, provides their own geometry to that data. Now for example, now this is a visualization of a file system on my laptop. So in this case, the yellow files, which are the DLL files, well, the DLL files are represented by yellow. So here you can see that this is my Windows directory. And the image files are generally represented by reds, like VMPs by reds, then JPEGs by pinks. And so I have a picture directory on my laptop. So this particular area represents the JPG files on my laptop, on my file structure. So this is another example of information visualization. So can you see the different color patterns on the dots here? Is that visible?
Yeah.
Okay. So this is another genre of visualization called as flow visualization. So here we are trying to represent a 2D slice from a supernova astrophysics data. And in this case, we are representing each data element by a dot. And the dot has colors, such that the dark blues and greens represent low velocity, and bright oranges and pinks represent high velocity. So I have a demo on this. So, So here we are trying to represent the flow patterns using dots, and we are also using animation techniques in order to show the direction of flow in the astrophysics data. So the user is zooming into the data. Zooming. So here you can see the bonus there of the data. Now the user is translating, zooming in again, translating to a different area. So here you can see the board is. This is an animation technique whereby at the end you can see the structure in the flow data. So this was flow visualization. So now another genre of visualization is the non-photorealistic visualization. So the image on the top here represents a photographic image, and this image represents non-photorealistic visualization. So whereby different kinds of brush strokes are used to represent the fine details in this particular photographic image. So what's the advantage of using a non-photorealistic technique compared to a photorealistic technique? Well, it has been found that the non-photorealistic techniques are more engaging, more effective. And you can also see the fine details. Now, for example, so these kind of fine details are evident from this kind of brush stroke than compared to if you just look in this area. So that's another advantage where non-photorealistic techniques are used in visualization. So let us talk a little bit about what are the different factors you need to consider in order to create perceptually salient visualizations. By perceptually, I mean by just looking at the visualizations, you can, thank you. By just looking at the visualizations, you can gain more understanding about the data within a few seconds rather than just scanning the image for a few minutes. So the factors that we take into consideration are different visualization techniques, that is the way the data attributes are mapped to different visual features, properties of the data, whether the size of the data, like how many elements are in the data, Then the dimensionality is how many attributes are in the data and the attribute range. Then also the user's tasks, what the user wants to do with those visualizations. It can be target search, boundary detection, boundary identification, tracking, estimating, so on. And the other two properties are the physical characteristics of the display device, which depend on display resolution, physical size, and the viewing distance. And the last property is acuity of the human visual system. That is the visual angle formed by that by a single element in the visualization at the back of the user's retina. And the field of view, which is the maximum number of degrees of visual angle that a display device. Now, a visualization is shown on a display device. So what's the maximum visual angle the display device forms on the back of a human's retina? So I'll talk about these in a little bit more detail in the next few slides. So a lot of research has been done in the first three areas, but not much on the last two areas. So the last two areas is my focus of PhD research. Okay, so I talked about it's important to decide what kind of visualization techniques you want to use. So the different types of visualization techniques are focus plus context techniques and overview plus detail techniques. So the way we use these techniques are based on the kind of data you have and the kind of visualizations you want to generate. The one on the left, which is the fisheye lens, which shows, I think it's the subway system in Washington, D.C. So here you can see that the center is focused, so you can see more details about three things. So at the center you can see more details, and as you move away from the center, the details get more or less and less. So that's an example of focus plus context technique. The other example is tree maps. So in this case, we are again trying to visualize a file system. So in this particular file system, there are three levels. So these tree maps are mostly used to represent hierarchical data. In our case, file system is a hierarchical data, so we are trying to represent that. Three levels. So the first level is 7 horizontal regions. So here you can see 1, 2, 3, 7. And then once these are partitioned, then you horizontally partition or you vertically partition each level. So in that way you represent the different levels in the file system. The other aspect is the properties of the data, that is the size of the data, the number of elements, the dimensionality, the number of attributes of each element, attribute range, and the user analysis tasks. So the different display device properties we need to take into consideration is the display resolution. Okay, so what is the maximum number of pixel size of the display device? And then the physical size. Because now let's say a PDA could have the same resolution as a Powerwall, but can you visualize the same data effectively on a PDA as compared to a Powerwall? Well, maybe not on a PDA, because the visual angle formed by each element on a PDA is going to be smaller on the back of the retina than compared to a Powerwall. So therefore, the physical size is important as well when we take.
What's a Powerwall?
Like a Powerwall could be like a cluster of monitors or a big display device with a high physical size and a high display resolution. In the range of about 4,000 by 3,000 pixels or something like that. And also the other factor that affects visualization is the viewing distance. For example, as you change the viewing distance from the user and the display device, the visual angle from the back of the retina changes as well. So there is a direct relation between the distance and the visual angle. So another example of showing how, so the acuity of the visual system is the measurement of our ability to see the details in a visualization. It depends on two factors: visual angle, the angle formed by a particular data element on the back of the retina. The other is the field of view, the maximum number of degrees that a display device forms on the back of the retina. Okay, So in the visualization pipeline image, I showed what we call as pre-attentive visual features. The different pre-attentive visual features that we can use in a visualization environment are color, such as hue and luminance, texture properties, such as height, size, orientation, and density. And you can see the variations of those in this particular image. You can also use different motion properties, such as flicker, directional motion, and velocity. And we map different attributes of the data set to these particular different visual features based on the perceptual guidelines that I talked about. So now let me move on to a few examples of visualization, like some visualization problems that I've tackled through my graduate school. This is some work I did for my master's thesis, and this was presented at the visualization conference last year. So here we are trying to visualize movie data using animation techniques. So just an overview of this project. Now this is a technique that allows viewers to compare multiple query results, which represent a subset of the data set. And we are trying to visualize multidimensional information along a space-filling spiral. Then we use graphical glyphs. Now by graphical glyphs, I mean simple geometric objects that are used to represent a data element. So I'll show a demonstration here, and then things will get more clear about this. We also use a clustering algorithm that is used, so that is applied on a user-chosen ranking attribute that bundles together similar data elements. Then this encapsulation is also used to show the relationships across different queries via animations. And then we apply these techniques to a movie lens recommender system. Now what is movie lens? So this is a system developed at University of Minnesota. What the system does is the user rates a bunch of movies that he has seen. Based on those ratings, the user gets a bunch of movies with their ratings that the user hasn't watched previously. So this is based on collaborative filtering technology. And so we used those results as our query results. So let me, I guess this image doesn't look too clear. So basically what this image shows is how the data is collected. So the user rates a bunch of movies in the movie lens system, gets a bunch of movies back from the system. Then we augment that data with some IMDb data, like the length of the movie, the genre of the movie. And then we combine these two data, and we get what we call as our query result, which we use as input to our visualization system. Yeah.
The movie lens stuff, is that pretty much just what Netflix does? I mean, very similar, I guess. I mean, is it basing all those results off of results from other
Yeah, I think
systems?
Blockbuster and
Yeah,
Netflix nowadays, they
pretty
use
similar.
the collaborating filtering
Yeah.
technology,
Okay.
whereby a user has his profile on there.
Okay.
That profile is matched with some other
Yeah.
user's profile who has seen those movies, which this initial user hasn't seen.
Yeah.
So based on those, matchings are made, and thereby that user gets the results back.
Gotcha.
So this is the entire design of this visualization technique. So we represent each movie with a 3D tower, whereby the height of the 3D tower represents the rating of the movie. The different genres of the movie are represented by tan-colored flags at different heights. Here I'm only representing 4 different genres of movies. Then there is a flag at the bottom which represents the year the movie was released in. The brighter, the newer the movie, the darker, the older the movie. Then the length of the movie is also represented by the luminance of this 3D tower. So now we have designed how to represent each movie using a graphical glyph. Now we still need to position those graphical glyphs in the visualization environment to make sense. So we have used a spiral technique, whereby as you move away from the center of the spiral, the rating of the movie decreases. So thereby, since the rating of the movie decreases, even the height of the glyph decreases. So here this is an example of like half a movie with still, this image is not pretty clear as to what this particular balloon shows. So let me move on to an animation technique. Just gonna keep this. Okay, so this is, so here I like to give an example. Let's say there are two users. They both want to go and watch a movie together. But one user doesn't know what the other's preferences are or one either the other way. So they go to the movie lens system, rate a bunch of movies, get some ratings back from the movie lens system. Same is the case for the other guys. So now we are trying to match those two ratings of these two different users and try and find out if there are any movies that are common between them. And if there are, which are the movies that they both would like to go and watch, rather than the user A likes it more, the user B doesn't like it so much, user A doesn't like it so much, user B likes it too much. So let's have a look at an animation of all this.
This video demonstrates our technique for visualizing results from queries into a multidimensional data source. Our goal is a technique that can highlight patterns both within and between query results. Our algorithms are made up of two parts. First, individual query results are visualized using multidimensional glyphs that vary their color, texture, and spatial location to represent different attribute values embedded in each data element. Second, animations are used to highlight similarities and differences between pairs of query results. The result is a combination of iconic and dynamic techniques designed to show patterns within a query and between pairs of queries, respectively.
So in this case, what I want to point out is this cluster of movies is moving from its position over here to its position over there. So what that means is the user rating of those cluster of movies for user A is higher than compared to user B. So this is a cluster of movies that user A likes more than user B. So similarly, we can make some conclusions about this entire data set. And these techniques can also be applied not just to movie data, but any kind of abstract data. So now this is another project I worked on during my summer internship last year with Network Appliance. And we also presented a paper on this at VDA conference and Supercomputing conference. So this is a visualization of storage controller performance data. So at Network Appliance, they basically build large amounts of storage controllers which store large amounts of data. So they run a variety of tests on these storage controllers, and these tests generate a large amount of log data, which can be in the form of binary data or text files and so on. With different characteristics, like different behavioral characteristics of the storage controllers, such as the number of reads per second, writes per second, disk utilization, CPU utilization, and so on and so forth. And so they run these variety of tests on the storage controllers from different time intervals. And what they want to find out is try and dig more into these log data and see if there are any anomalies in the data, or if the storage controller is performing in some weird fashion, or if something's working right, whatnot, by changing the different characteristics of the data, of the storage controller. So this is a technique that visually analyzes a storage controller's performance, use graphical glyphs, 3D objects to represent the log data for important loads, build a graphical glyph, how to place the graphical glyphs in the visualization environment, and then compare the storage controller's performance at different time intervals. So this is a block diagram of a storage controller of network appliance. So we don't have to go into the details about it. This just shows how the data, how the log data was collected. So there is an abstraction layer called as counter manager, which extracts the data from, well, so you can consider this as a black box of storage controller. So the counter manager is an abstraction layer which separates the storage controller and the APIs that grab the amount of, or that grab the log data in the form of binary log data or text files. And this is provided as an input to our visualization tool. I don't want to go into the details of how we came up with the design. So we came up with different glyph representations. Now you can have 3D glyphs, 2D glyphs, or just 2D square glyphs. Each one has its advantages and disadvantages, which are listed there. 3D glyphs have more surface area, so they can represent more amount of information. 2D glyphs cannot do that, but then 3D glyphs have the problem that they cause occlusion. But then with intelligent camera panning techniques and the way how you pan or zoom, like you can overcome that problem of 3D glyphs. So we came up with two placement algorithms. One is a traditional 2D grid layout whereby you map one attribute to the x-axis, one attribute to the y-axis, or you can also use the spiral technique that I talked about previously. So this is the different kind of data feature mappings we came up with. So here you can see like U was mapped to CPU reads, luminance mapped to port transfers, size to user reads, orientation to user write blocks.
What program did you use to create these?
So I used like VC++ to code this, and for graphics I used the OpenGL APIs.
Wow.
And for the user interface I use TickleTK, which is cross-platform independent, so you can run the tool on Windows as well as on Unix machines.
So there's nothing like a crystal reports for 3D mapping or anything like that. I mean, it's a graphical mapping. I mean, because it seems like this is fairly scientific and straightforward. You figured somebody would come up with a tool that could do this better than like Excel or something.
Yeah. See, but then like different users have different analysis, also different tasks, what to do with that data. So those two, like there are tools available in the industry, but then those are specific for their own purposes. And here, like we want to build flexible tools which you can use for different purposes as well, with different data sets as well. So that's one of the reasons why we build our own tools.
Wow.
So let me provide an example of visualizing performance data. Now let's say we are trying to visualize NFS writes workload to a storage controller. So the NetApp storage controller's cache writes, enabling immediate acknowledgements back to the disk. This results in low overall response times. Then dirty data is periodically asynchronous flushed to the disk. An event called as consistency point. Consistency point increases the CPU and disk utilization. So in this case, once again, we are using 3 metrics called graphical glyphs to represent 1 second of workload on the storage controller. And as I talked about before, we are representing this data set on a traditional 2D grid or a spiral. So this is a visualization of the NFS writes workload on a storage controller. So let me tell you the mappings. Well, the mappings are also there in the legend here, but the x-axis and the size of each glyph represents the throughput. The y-axis represents CPU utilization. The height of that particular glyph represents response time, and the orientation represents disk utilization. So in this particular visualization, I want to point out 3 areas of interest. So one is this area where the throughput is high as the x-axis is high, size is large as well as compared to these ones. So these are kind of ideal conditions where the height of these glyphs is small, that is the response time is low. So these are ideal conditions. The exact opposite conditions are present here over here, where the response time is high, the throughput is low, and the CPU utilization is high. So there is a third condition I would like to talk about. This is a sample within a consistency point. So here you can see that the orientations, by orientations I mean each glyph is like oriented in a different way. So it's starting from 0 degrees to 85 degrees. So here you can see quite a bit of variation amongst them. The glyphs are kind of clustered here. So those represent samples within a consistency point. So this is an area where the data is being written back to the disk. So let me show the exact same visualization. Instead of a traditional 2D grid, we are doing that on a spiral layout. So here you can see the same data set is represented in a spiral layout. So why a spiral instead of a 2D grid? So one of the advantages of a spiral technique is that it helps the user to see like repeating patterns. And some people also believe that, okay, spiral technique is an efficient use of the screen space. I don't necessarily agree to that, but so here you can see a repeating pattern of brown low glyphs over here. So that represents when the data is which represents low disk utilization and low response times, followed by a temporary increase in the response time by red colors, and then once again a blue pattern whereby the data is being written back to the disk. So you can see brown, red, blue, brown, red, blue. So this pattern keeps on repeating. So similarly, you can do comparison of the performance data. That is, so you can compare the log data at 2 different time intervals, and you can compare that using 2D grid techniques as well as spiral techniques. So this is a comparison of 2 different time intervals, where the different time intervals is represented by different hues. So this is a serial layout. By the serial layout, well, the serial layout helps us in gaining an overall understanding, an overall picture of the performance of the storage controller. And this is whereby, well, this is a parallel layout of the same data. So whereby at each, and the x-axis represents timestamp. So for each axis, you can compare the 2 different values. I guess this looks a little messy than how I would like it to be. But one of the conditions for the people I work for at NetApp is that they want to see the entire data set at one screenshot. They don't want to take any data off the screen. So this is how we had to come up with. So the same is the case for a spiral layout. So this is a serial layout starting with the blue and then the red, which represents 2 different time intervals. Same is the case for the parallel layouts. So now finally I would like to talk about another project I worked on is visualization of software architecture. So this work is going to be presented at WizSoft and MSV in a couple of months. So what are we trying to do over here? So in this project, we are trying to visualize data on tap, which is storage server operating system at Network Appliance, using MDS technique. MDS technique is a technique used to represent high-dimensional data in a low-dimensional environment. Once again, we use graphical glyphs. Then using these results, the display allows the viewers to rapidly and accurately analyze the data. So how do we do this? So we have the entire operating system. We take the source code of that. There's a tool called Understand C++. I don't know if you guys have ever worked with that. But then basically what that tool does is that it kind of compartmentalizes the different components in the operating system. So we ran the Understand C++ tool on data on tap operating system. We came up with 38 software components, and we're trying to represent, or trying to visualize these 38 software components. So this gives a laundry list of how we went through the process. So this is how the source code was quantized to different components. You can see, so the different attributes of this particular data was the number of files, number of global functions, variable functions, local functions, and so on. So what is MDS technique? NDS technique is a technique that provides visual representation of pattern of proximities among a set of objects. The relationship between input proximities and the distances can be positive. For example, in the case of visualization of cities, so the larger the distance, the larger apart they should be placed. And negative distances, the way that we used for visualizing software architecture was the higher the number of correlation between two software components, the closer they should be placed, and vice versa. So this is a technique. I don't want to go into the details about this. So this is a visualization of cities. We tried to approach this problem, trying to first come up with a solution for this small problem. We are trying to visualize 9 cities. So let me show a video about this. So this gives a fairly good illustration about the NDS technique. So here the user gets, so you randomly place all the cities, and through each step, which is a stress function, you change the values which closely correspond to the final values that they should attain. So as you can see, the cities are moving closer or moving further apart at each step. Because I'm running short of time, I'm just going to get to the point that I'm going to illustrate here. So here the cities have reached their final states, but as you can see, this doesn't look topographically accurate. So I'm trying to rotate, translate, or somehow convert this mapping in such a way that it would represent geographical data, to come up with a topographically accurate representation of these 9 cities. This was one of my friends trying to use my tool, so it didn't know how to rotate or translate, so it was okay. So we came up with a solution for the cities. So we applied a similar approach to the visualization of 38 software components.
Oh, so what that visualization on the previous slide, what that visualization was taking the distance from each of the cities to each other. You had to automatically figure out where they were all at.
Right.
Wow.
So basically, what you can consider, so this data set, that is the distances amongst the cities, can be considered as a multidimensional data set. So we used this same principle to our software data set, our software component data set.
Wow.
I don't want to go into the details about it. So here we are trying to visualize the global function cross-reference table. So you have these different software, well, so this is a subset of this particular table, which consists of 38 software components. So this part is the cross-reference table, and then we also have additional attributes of each component, which is the number of files, number of threads, number of global functions, variable functions, hardware distance, and so on. So here we come up with a mesh, which is kind of messy, but still, in this case, you can see that the graph is not complete. So it still gives you some information about the relationship between software components. And this is an outgoing connections from software component platform to whatever components it is related to. So what this visualization shows is that, okay, software component platform is connected to storage, to photos, and snaps, and so whichever components it is being connected to. Okay, so those are the components, they are related. The line, the distance amongst those components represent how correlated those two components are. Even the line thickness, so here you can see the line is thick, here you can see it's not so thick. Even that represents how correlated those two software components are. Similarly, we did for global variables. So I have a video about this, but I don't know how much time I have.
About 5 minutes.
Okay. So this is an 8-minute video, but I guess I'll skip to the points where So once again, the user captures the data. So these are the 38 software components. They are randomly positioned right now anywhere based on their initial settings. Then we iterate through the process. So this is the application of the MDS technique, whereby this 38 software components are coming to their final state. So one of the confusing aspects about this for the performance engineers at Network Appliance was that, okay, why don't you initially just start where none of the visual features are mapped to any attributes? Just start with the, okay, so start with this and then let the user change the mappings to whatever visual features he wants to be mapped, whatever attributes he wants to. So this is an illustration about how different visual features are mapped to the different attributes of data. So I'm just gonna go through this quickly. So now the user is mapping different attributes to height. Similarly, now the user is mapping size to different attributes. Orientation is mapped to different attributes. So this is just an illustration about how different attributes can be mapped to different visual features. Thereby, the user gains more understanding about those visual features or those attributes. So this is the messy mesh I was talking about before. So you can click on each balloon and it gives you more information about that software component. So now I have selected a single mode whereby you can click on each software component and it's going to show its relationship with other software components in the software architecture. This is all I wanted to show about this. So you might ask, so why do I care about this? Okay, you have 38 software components. You are showing the relationships from one component to other. So why is that important? Because generally, like in an engineering company such as Network Appliance, they have different engineering teams which have different modules. So this visualization tool helps them see how my module is connected to some other module. So basically this visualization gives that person an overall picture about the software architecture of the entire operating system, which as such is kind of huge. So this helps the performance engineer or even the software architects when they're trying to design software schemas for maybe for an operating system or for different kind of tools, some perspective about how to design or how to go about the design of the software architecture. Then this tool also helps them evaluate the progress of the software architecture. Whether, okay, this module is connected to this, but maybe this shouldn't be connected to this, which can be seen using this visualization tool. So that helps in evaluating the software architecture. Okay, so in this case, we have developed an automated software architecture using raw source code as input. We use rules of human perception to build displays that harness the strengths and avoids the limitations of human vision system. And once again, our techniques are not restricted just to software architecture data. It can be applied in any situation where the distances amongst the objects can be easily controlled by the glyph placements. So finally, I would like to talk about future directions. So there was a paper by Johnson, 2004. So there is always a debate whether visualization is a science or whether it's an art. So my perspective about it is that it's a combination of both. It's science as well as art. So quantify effectiveness. Like in an example that I provided before, like non-photorealistic technique. So I said that, okay, the non-photorealistic techniques are effective, more engaging. So how do you quantify that effectiveness? So there are studies about that going on. And then, so this is a hot topic right now in visualization, uncertainty visualization, whereby uncertainty in the data is trying to be visualized by different researchers. Then the perceptual issues, that's the display hierarchies. Then how you can use like different hardware systems, such as distributed like hardware systems. Then the different hardware, such as graphics processors, how they can be combined in order to gain more understanding. HCI techniques, then feature detection, and well, visual analytics is another branch of visualization that has come up with. And there's always research going on about different theories of visualization. There is a kind of dichotomy between scientific-based people and info-based people. They always debate which is better, which is not. So I just feel that they are two different kinds. They have their own place. Finally, I would like to acknowledge my advisor, Christopher Healy, my colleagues, and some of the people I worked with at Network Appliance. And thank you.